Good morning. Now today we are going to start a new module, that is Unit 4, Magnetic Properties of Solids. So in this module, on certain topics I will upload classes, whereas on some other topics which are easy to understand I will be uploading only notes as PDF file. Okay. So first topic is about quantum theory of paramagnetism. So before learning quantum theory, let us revise what paramagnetism is. This you might have learned in your degree classes. So paramagnetism is mainly seen in atoms, ions and molecules that have permanent magnetic moment. Now, in the absence of magnetic field, how will be these magnetic moments? They will be in random orientation, so there will not be any magnetization. But when you apply magnetic field, what happens to these moments? They will orient themselves in a particular direction, that is, they will orient in the direction of the applied field. So you will get a magnetization, and the direction of that magnetization will be parallel to the applied magnetic field. Okay. Now for paramagnetic materials, the susceptibility is small, positive and temperature dependent. The permanent magnetic moment of ions mainly results from spin moment or intrinsic moment of electrons, orbital motion of electrons, spin magnetic moment of nucleus. These are the three sources from which the permanent magnetic moment of ions comes from. Paramagnetism is mainly seen in metals, atoms and molecules having odd number of electrons like free sodium atoms, gaseous nitric oxide, etc. Then few compounds having even number of electrons like oxygen molecule. Then free atoms and ions having partly filled inner shell, that is rarer than the actinide elements. Ions or some transition elements like Mn2+. So these are the materials that exhibit the phenomenon of paramagnetism. Now let us learn about the theory, quantum theory of paramagnetism. So these are just theory part, we will read it long, but in between you need to learn some expressions. That is the only a difficult thing. These and all are simple to learn. Now according to quantum theory, magnetic moments are quantized, that you know. The magnetic dipole moment, that is mu, and its component in the direction of the applied field, that is mu z, cannot have arbitrary values. So generally we write a relationship between this magnetic dipole moment mu of the atom and its angular momentum capital letter J, and that relation is given by equation 1. Mu is equal to minus G mu B J. Here mu B is nothing but Bohr magneton, and it is given by E h cut by 2m. Okay, and the small letter G is known as Landé G factor, and its value is equal to 2 if net angular momentum of the dipole is due to electron spin, and its value will be 1 if it is due to orbital motion. So G is the Landé G factor. Its value will be equal to 2 if its origin is due to electron spin, and its value will be equal to 1 if its origin is due to orbital motion of the electron. Okay, value will be 2 if it is due to spin motion of electron, and its value will be 1 if it is due to orbital motion of the electron. And the expression for this Landé G factor is given by G is equal to 1 plus J, J plus 1 plus S, S plus 1 minus L, L plus 1 by 2 J, J plus 1. This formula is very important. You may have to use this formula in solving problems. So here what is J? J is the total angular momentum of the atom. Okay, what is S and L? S is the spin quantum number of the dipole, and L is the orbital quantum number of the dipole. Okay, now about this Landé G factor, we will learn more. That is your another topic. I will upload a note on that in LMS. Okay, about Landé G factor. That is, it is something related to crystal field splitting, and it is also termed as spectroscopic splitting factor. This one, Landé G factor or G factor. So on both this crystal field splitting and spectroscopic splitting factor is also a part of your syllabus. Okay, that I will upload it as new notes. Now, the orientation of magnetic moment mu with respect to direction of applied magnetic field is given by this. So here we are applying the field in the z direction. So the component of magnetic moment in the applied field will be mu z, and its value is given by minus g mu b mj. G, you know, it is Landau G factor. Mu b, Bohr-Manton, we have just discussed. Now what is the small letter mj? It is the magnetic quantum number associated with the total angular momentum of the atom, capital letter J, and it can have values from minus j to plus j. Okay, that is, it can have 2j plus 1 values, which means that magnetic moment of the atom can have 2j plus 1 different orientations related to the field. That is the meaning. Okay, this mu j is that is, this mj is nothing but magnetic quantum number associated with the j. It can have values from minus j to plus j. That means it can have 2j plus 1 values. That is, mj can have 2j plus 1 values, which again means that mj can have 2j plus 1 different orientations related to the field. Hope it is clear. Now, next portion. The potential energy of such a magnetic dipole in the presence of magnetic field B is given by this expression, that is E is equal to mj g mu b b. Okay. Now, according to MB distribution, that is Maxwell-Boltzmann distribution, the expression for the number of atoms having a particular value of mg is proportional to this. That is E raised to minus of this particular quantity, C, minus mj g mu b b divided by kt. So, the number of atoms having a particular value of mj is proportional to e raised to minus of this expression divided by kt. This e raised by kt, where e is equal to this one. Then you will get this expression. Okay, so learn this expression. Considering a unit volume of parametric material, that is, you just consider a unit volume of parametric material containing a total of n number of atoms. Then magnetization, capital letter M, in the direction of the field, capital letter B, is given by M is equal to n into statistical average of magnetic moment component per atom along B. Okay, n is written here. Now this is the expression for statistical average of the magnetic moment component per atom along B. So that expression you will have to learn. But you can study it very easily. That is, first look, the summation is from mj from minus j to plus j, that we have already discussed. It can have values from minus j to plus j, right? Now, next, in the denominator, what you can see is e raised to minus of this particular quantity that we have already discussed. This one, this term is written as the denominator, and on the numerator again you are writing that same term, erase that particular term, but along with that you have some additional term. What is it? Minus mj g mu b. Okay, so like that you just study those expressions. Now we consider two cases. So keep in mind equation 5. Now we are going to discuss about two cases based on equation 5. First case is at normal flux densities and ordinary temperature. In that case, the argument of this exponential, that is mj g mu b b by kt, is very less compared to 1. See, this is the argument, right? So at normal flux density and ordinary temperature, we assume that the argument of exponential, that is this one, is very much small compared to 1. Then how will be your equation 5 look like? Your equation 5 will now reduce to n is kept as such, m is equal to n, g mu b is taken outside. This one is kept as such, summation. Now see, just a modification is there. Minus mj is also kept as such. Now since this particular argument of exponential is very much small compared to 1, that exponential term will now reduce to minus mj g mu b b by kt. Okay, see, that is the only thing. That is, whenever you come across e raised to this particular term, e raised to minus of this term, e raised to minus this one is replaced by this one, 1 minus mj g mu b b by kt, because this is the condition applied. Okay, so just compare the subsequent equations and learn, then it will be easy. Now we make two assumptions, that is summation from mj minus j to plus j of mj is 0, and another one is summation mj from minus j to plus j, mj square is having this value 2. That is, when this summation is from minus j to plus j. Now when that becomes from 0 to j, then you will multiply it with a 2 that you have studied in your maths classes. Then mj square is written as such. That is, you are just changing the summation part. That is, you are changing the summation of mj from minus j to plus j to mj from 0 to j. So when you are changing that limit, you have to multiply with the 2. That is why 2 appears here. Mj square is written as such. Its value is j plus 1, 2j plus 1 by 3. Okay, so you are making two assumptions. Summation of mj from minus j to plus j is 0, and summation of minus j to plus j mj square is equal to j plus 1, 2j plus 1 by 3. Therefore, applying these two conditions, the above expression for m will now reduce to this. Okay, just apply those two relations. Then it is again equal to 2j plus 1 and 2j plus 1 will get cancelled. So you will get equation 6, m is equal to n g square mu b square b by 3 kt j plus 1. Okay, this one and this one get cancelled. So equation 6. Now parametric susceptibility, that is chi para, is equal to here you have the expression for m, right? M into mu 0 by b. That is the expression for parametric susceptibility, that is mu 0 m by b. So here you have the expression for m. Now what you have to do, you just multiply with the mu 0 and divide it with the b. Okay, when you divide it with b, there is a b here, so b and b get cancelled. Okay, so your expression will be equation 7. Now see, again equation 7 is again simplified to mu 0 kept as such, n kept as such, mu b square kept as such, 3 kt kept as such. Now here you have seen an additional term, that is p effective square. It is nothing but effective number of Bohr manifold. It is g of root j plus 1. See here you can see this one, right? So that term is replaced with the p effective square. Okay, because p effective equal to g into root of j plus 1. So your final expression for parametric susceptibility is equation 8. So that is the first case. Now the second case, that is at low temperature and strong magnetic field, then the argument of the exponential, this one, is not smaller than unity, and it is not possible to make a series expansion of the exponential term in equation 5. In the earlier case, we have assumed this to be very small compared to 1. Now in second case, this one is not smaller than unity. So your equation 5 will now reduce to a new form. Study this one. M is equal to n g j mu b. A new one comes, that is bjx. It is nothing but Brillouin function. Okay, and the x that is written here is g j mu b b by kt. So in this topic you will come across many such expressions and its substitution, so that there is no other way, you just have to learn. Okay, so bjx. So now in the second case, the expression for m is n g j mu b bjx, where bjx is a Brillouin function. And Brillouin function, if you want, you can again write this expression. Okay, bjx is equal to 2j plus 1 by 2j cot h 2j plus 1 by 2j x minus 1 by 2j cot h x by 2j. That x is g j mu b b by kt. So all these expressions you will have to learn because there is no other proof and all. Just mention that is enough. Okay, so this is your expression for m. Here bjx is a Brillouin function. It is given by this, where x is this. Okay, now for x very much small compared to 1, then this one cot hx will approximately become 1 by x plus x plus 3. Then the above expression, that is 11 bjx, will become x into j plus 1 by 3j. Okay, then as usual, parametric susceptibility, what is this expression? Mu 0 m by b. It will become mu 0. What is your expression for m? M was n j plus 1 g square, that is p effective square mu b square by 3 kt. Right, so it will be equal to mu 0 n p effective square mu b square by 3 kt. So susceptibility's expression will be this, equation 12, and it is the same as equation 8. Just compare and see. Now this is for the case when x is very small compared to 1. This is your expression for parametric susceptibility. Now for x very much large compared to 1, that is at low temperature and strong field, what happens? Cot hx is approximately equal to 1 and bjx will be equal to 1. When x was very small compared to 1, what was it? Cot hx was 1 by x plus x plus 3 and bjx was x into j plus 1 by 3j. Okay, now when x is very much large compared to 1, then cot hx will be equal to 1 and bjx will be equal to 1. Then your equation 10 will become, what was your equation 10? M is equal to n g j mu b bjx. Now bjx is 1. So your equation 10 will now become m is equal to n g j mu b. See, that is equation 30. This result implies the state of magnetic saturation, which means all dipoles will be aligned in the direction of the applied magnetic field B. Now when J is tends to infinity, that is for a large number of orientations, then the expression for cot h 1 plus 2jx will reduce to cot hx, cot hx. Okay, and bjx will be this one. So I think there is no need of explaining that. You can just leave it. That is they have mentioned just to show that class quantum approaches classical one. So I think no need of mentioning that. So this part you can skip. Okay, now the order of parametric susceptibility of a solid can be estimated from equation 12, that is from this equation 12. Okay, you can calculate the value of parametric susceptibility at room temperature, and its value is approximately about 10 raised to minus 7, which is very small. Now it can be increased by more than 100 times at 1 Kelvin. So equation 12 is successfully employed to predict the values of susceptibility for various parametric crystals, particularly rare earth ions. The value of J is determined by applying Hund's rule, that we will discuss later. I will upload a note on Hund's rule. Okay. However, equation 12 is unable to account for the experimental observations of susceptibility for the ions of ion group. Okay. Equation 12 is valid only in the case of parametric materials. That is, it is used only for evaluating the susceptibility of parametric crystals, but it is not found successful in the calculation of susceptibility for the ions of ion group. Okay, so in this essay, we can write from the very beginning. There is not much confusing in the first two slides. Here also it's okay. Here in this slide you will have to study a few expressions. That is, this one you will have to learn by heart, and the other everything you can solve. It's very easy. Then yeah, this one bjx, this expression also you need to study. Then the two cases when x is very much small compared to 1 and x very large compared to 1. This session, as I said, you can skip that from here. Okay, the last paragraph you can write. Okay, now here they are mentioning about a reason why this one, that is equation 12, cannot be used to calculate the susceptibility of ions of ion group. The reason is mentioned here. It is best because of the presence of crystal field, that is crystal field splitting. That also I will upload as notes, because in that case we cannot neglect crystal field due to other ions which cannot be neglected in comparison with the externally applied field. That is, there the effect of crystal field comes. So using this simple equation we will not be able to calculate the susceptibility of ions of ion group. Okay, just because of the influence of crystal field. Now equation 12 uh, holds good in some cases, but when it becomes so strong, what happens is that it will break the rotational symmetry of the dipole, and it will affect the total angular momentum, capital letter J. Also, the average value of orbital angular momentum, that is L, will become 0. That is, L value will become 0. That is called quenching of orbital angular momentum. Okay, so these are some factors that hinders us from the use of the equation to calculate susceptibility of ions of ion group. Okay, uh, so next, in such cases our equation 4 can be written as E is equal to 2 ms mu bb. What is your equation 4? This one, E is equal to mjg mu bb, is now will written as g value will become 2. Why g value become 2? Because the g value is 2 because of the spin motion of the electron. So it will be 2. Instead of mj you are writing ms, because spin motion you are considering. Mu bb is kept as such. Now ms b is mu b e h cut by a. Okay, that is here 2 ms mu b b. 2 ms mu b means e h cut by 2m b. 2 get cancelled, so it will be ms e h cut by mb. Okay, now for this condition, if it is very much small compared to a Boltzmann constant in temperature kT, then your expression for chi will become like this. So this formula is mainly used to calculate the susceptibility for transition metal ions like Mn2 plus. Okay, so this slide I just showed you just for your information. For your essay and all, no need of writing this slide. Okay, you can stop your essay here. Okay, thank you.